Good morning, welcome. We start now our third week. We have a couple of things this morning I showed here on the slides that we will discuss. We go a little bit deeper into this notion of receptive fields, filters, kernels, to really understand what they do. We saw last week that the primary function of the filters we see in V1 is extracting differential structure, not only edges, but also curvature. This morning we go look at differential color structure. So what do we mean with all these colored receptive fields? We have RGB processing, we have red, green, blue cones, but how are these actually processed? And we do not see red or green receptive fields, but we see differential receptive fields. So how can we take derivatives with color? That's actually what we discuss in the first part of this morning. Then we really go into the mechanics of deep learning. How is backpropagation working? And we take a very detailed numerical example on what is actually calculated, how does the process go backwards, what is the mathematics behind it. We will look at it's actually the differentiability of these layers. We need a chain rule to go backwards, and we go a little bit in depth to show how this is working. So then you give a little bit more about the machinery. And we go talk about face recognition. How is it working? What's actually done with face recognition? What features are detected? How is it working? And we will see that we need to have, intensity invariant properties from face detection. So we're going to look at histogram of gradients and go a little bit more specific. And the last part I spent on another type of kernels, and these are temporal kernels, because all the receptive fields in your visual system are not constant. They dance around, and they change every millisecond. That makes the world quite complicated. So why is that temporal structure? So that's what we do in the third hour. So let's first rehearse some physiology. This is the visual system, as I showed you now many times. From the retina, we see there's a lot of processing already there. We go to the first synaptic station, that's in the thalamus, in the area that's called the lateral geniculate nucleus. It's this small nucleus. It has 6 layers, and you see 4 layers have small nuclei. These are parvonuclear, and 2 layers have large cells, and these are magnocellular. The magnocellular, they take part in the motion channel, and the 4 other ones take part of the shape channel. Why do we have 4 channels? Well, it's not exactly known, but all measurements look like that. This is clear. This is the left eye, this is the right eye, left eye, right eye, and these are the on channels, and these are the off channels. So that is the, and here we have the motion channels. 20% of what is going from the thalamus is not going to the cortex, but is going to the pretectum, and that is an area that's called the superior colliculus. And the superior colliculus is a very important part, and nowadays very much studied for all detection of motion, but also prediction of motion, the prediction of eye movements. So if you have, for example, you have to make directional eye movements, where do you go? It's all planned and programmed in the superior colliculus. It is a major step. It is in the deep brain right here. Well, all this processing, they have pretty ill-defined on and off, so they respond to almost any visual stimulus, regardless of shape, color, or orientation, but they look at motion. So it doesn't matter exactly what it is, but it is more where is it and how is it moving. If people have damage here, they can have all kinds of strange eye movements or no eye movements, and the projections are mostly from the large cells, so the motion-sensitive magnocellular projections. A rehearsal about the LGN, the lateral geniculate nucleus. We remembered that the retina was split with a horizontal line that the right side of the retina goes to another brain half than the left side of the retina. So somewhere in the middle it has to be connected, so we have huge connections in the middle of the brain that connect the left and the right eye. But it means that the right visual field in both eyes is going to the same, is going to the opposite half of the brain. Well, here it goes to the layers in the LGN, the 6 layers. You call them contralateral and ipsilateral. That's clear. Ipsilateral is on the same side and contralateral is on the other side. And then it projects. We have what's called the magnocellular pathway and the parvocellular pathway and these different layers. And what happens in the LGN? They have similar receptive fields as the retinal ganglion cells. So we remember these were the centers around receptive fields. So in LGN, we do not have these differential cells, like the simple cells. So we do not take derivatives or so. So there is no, let's say, geometry extraction in LGN. But the parvocellular layers, they have cells that respond differentially to color. And what does it mean, differentially to color? They're called color opponent cells because they have 2 areas, or 3 or 4, and they're mostly red, green, or blue, yellow. And we're going to see how that is working. And most of the cells are getting input from the parvo type, the P type. And magnocellular layers are colorblind, and they receive input mostly from the M types, and so they do not look at color, but they look at velocity. So it's actually an interesting idea. We have, and we will see that next week in much more detail. The retina is not just a camera, but the retina is a multi-channel device. It picks from every pixel a lot of properties, and it's not working at a high resolution, but it's actually working at a very low resolution. But it picks differential structure, it picks color differential structure, it picks motion structure. So there are separate channels going backwards. So motion, shape, color, and then we have depth, disparity. So all these channels, and these channels make a very rich feature set from pixels. So you get a whole stack of properties, and that's actually a cortical column. So a cortical column is a representation of a tensor. That is the big representation what you have, why we have all these stacks of filters in deep learning. You see them in the brain. And then you have to connect, well, if I have these tensors, how can they group together in a perceptual grouping and form a particular object? So we have to look at what is the connectivity between these tensors, and we're going to look in next week how these more complex structures look like. So we're now in the phase of making these complex structures. It's also quite amazing that the representation of color is completely different from the representation of shape. We do not have RGB processing like we do in our computers, which is actually quite stupid. We have 3 times more computer power, and the brain doesn't do that. So we have to look at is something more simple possible. If you look in the cortex, we remember we had these columns, but these columns were scheduled in, or arranged in hypercolumns with a pinwheel structure. You have the bands, left, right, left bands, and in the middle you have then these pinwheel structures, so it's a whole array of pinwheel structures in each band. And in these bands you have very tiny areas that are called the blobs, and only the blobs, the very tiny areas, they are color sensitive. So it's quite regional. And these blobs, they are found by staining. This is the cortex, and it was stained. It's in a monkey. It's from a paper, New World Monkey, Callitrix jacus. And here you see the cortex, and it's pretty amazing. There are actually only several dozen of these cortical, these color blobs, and they were found by staining with cytochrome oxidase. So they're also called CO blobs or cytochrome oxidase blobs. And that's a specific enzyme that gives a coloring staining, and you can actually see them. This is done by optical imaging, and you see how wonderfully you can actually see these anatomical measures. People have, of course, wondered, if you have these blobs, and you see the blobs outlined here, do they have a relation with the centers of these pinwheels? Are they maybe related to these pinwheels? No, they're not. So they seem to have a completely independent distribution. The red dots indicate the center of the pinwheels, and here the gray areas are the blobs, and you see there is no relation, and people have done some statistics on it. So there's a different tiling of color and this orientation space. So let's go back to our familiar figure where we have these stages in our deep learning cascade and the visual system cascade. We look at those first stages. And this is the set of filters that was published by Krzyzewski that he measured as output from a deep learning system after training it for a long time. And you see we recognize now most of these filters as filters that have these derivative of Gaussian structure. They come at all orientations. And here you see the color differential structure. So quite interesting, a red-green cell and a blue-yellow cell. So how do we get those cells? That's actually, can we understand those colored filters? And I go now spend the next 10, 15 minutes on explaining that. It's in a different PPT. It's called color differential structure. And let's look at color differential structure. This is an example. To the right, you see the color space, the RGB. If you put it in 3 dimensions, you can put all these nice colors. But what I mean with color gradients is that I really look at not intensity gradients, but how much is the spectrum, the spectral edge. So what is the edge in the wavelength domain? So here we see an intensity edge, and you see that the intensity of this red and green is more or less the same. So if I look at the gray values, it's more or less impossible to find them. You see them because it's red and green. If you take red-green edges, you much better see the contours of the outlines. Let's do some physics. If you look at some object, there's a lot that determines the color. Of course, the light source. And we have now the color temperature. We all know if you buy different lamps, LED lamps, 2700 Kelvin and so on, that's warm light. You have the intensity of the illumination. You have the sensor sensitivity. In this case, it's our eye. But it's also derivative it is dependent on the angle of incidence and the angle of reflection. So you have what's called the bidirectional reflection coefficient. If light comes in, there's some intensity change if it goes out. That's what we call the surface reflectance properties. Well, we take some simple examples in the calculations that I go do. The scene is uniformly illuminated, the light source is colored, and the surface has a Lambertian reflection. That means that it is, if there's light hitting in this place, the light goes uniformly in all different directions. So that is the most simple. It's not a mirror, it's just the opposite as a mirror. It is the most opaque surface you can think of. Well, we have the spectrum. This is the visible light. It goes from, this is a long wavelength, this is a short wavelength. More or less you can say that it goes from 400 nanometers to 800 nanometers. And we have, a arbitrary spectrum of light. You can have more reddish or more yellowish or whatever. If you take a heated object, like the old-fashioned light bulbs had, you see that if you have a very hot object, you get very short wavelengths. And if you make it not so hot, you go more to the reddish, and we all know that very well from experience. So if you have light sources at 2,500 K, 6,500 K, or 10,000 K, you have different. This has very much reddish, because it has the low temperature has high has very long wavelengths, and here we have a more bluish light source. What we go do, and this afternoon we go do it ourselves, is PCA on color images. And that's exactly the same as PCA on regular images. We have one complication. We take these patches, you remember from last week, 12 by 12 pixels, or 10 by 10, or anything. And what you do is, with this small patch, you make it in one long column vector. All these column vectors together, they form a matrix, and we do PCA on that matrix. We make the matrix square by multiplying it by its transpose, but that's essentially what we do. And the unfolding process is quite critical. So if you have 12 by 12 and you unfold it in a long column vector, at the end, after PCA, you get 144 long eigenvectors. You need to refold them again and chop them up. It's called partition in 12 by 12. And then you get these filters. Now we have color images. So what you could do with the unfolding, I have now 3 times 144. So do I do RRR from... There are 2 ways to do it. You can say, well, from every pixel, I stack them in one column, RGB, 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 or you say, I take all the R's, all the B's, and all the G's. Experiment with this afternoon. It's quite nice. It's just a one-liner in some experiments, and then you see what happens. But after unfolding in a 3 times 144 vector, you make another matrix, you do the PCA, and you chop them up in exactly the same way. We saw that we got, if you have restricted inputs, you got restricted filters. You remember the movie of the cat. And these are the filters that you get if you take an arbitrary color image. So I took a face. It's Anna Villanova, one of my previous staff members. And to the left, a nice doll. And what you see is differential color receptive fields. And these are the filters that we're going to apply, and we're going to see, can they also be used in a nice mathematical framework? Can we find some invariance that we say we want to be independent of all these physical properties that we had? So this is no longer geometry. Now we say, can we be independent of the type of light source? Because I recognize your color of your shirt, the independent, if you have fluorescent light or daylight, they're completely different light sources, but we have still some color constancies and so on. So red is red even in different situations and illuminations and shadows. So here we see them, and we see that they come in different orders. This is typically a first-order derivative. This is zero-order derivative. This is a kind of Laplacian filter. Here we have a higher order. Here you see we really go to high orders. So there's a lot of differential structure, and we have color and intensity together. This is only intensity. So here we look at edges without looking at the color. This is just the plain intensity. If you look at differential structure in the X domain, the space domain, and the lambda domain, you can say, okay, I can also take derivatives to lambda. And Koenderink was the first one who said that gives us a very nice framework. Let's have a look how this is going to work. So if you have no lambda, zero order, you have only derivative to x, you get these zero order, that's just a Gaussian, first order in x and y, all kind of second order derivatives. But the first order turns out to be, if you take the first order in terms of intensity, in terms of color, it is the yellow-blue one. And the second order is the red-green one. And then you can combine them with spatial derivatives. So here you have yellow-blue with first-order derivatives. So this is an intensity-color derivative. So you take 2 times the derivative. You see, lambda is 1 and x is 1. Here you take 2 times the derivative to color and 1 time the derivative to x. So you see, this is an edge detector, but it takes also the second derivative of the color. What does it mean? Well, we saw that color is represented not evenly in the retina. We have red and blue, red and green are more or less the same, but blue is very sparse. It's about 10% of all the cones. And if you look at the connectivity, we today know exactly how all these rods and cones are connected to one single receptive field of a ganglion. That's quite amazing. We can actually look so sharp in the retina, and I'm going to tell you more about this technique. It's called adaptive optics, and we can measure that together with the local connectivities. These papers are nice to see if you want to go a little bit deeper in how it was done. It's a famous Nature paper from 2010. And it seems that one receptive field has one blue cone. So you see that actually here. And this is the color blindness. Well, we saw this before. Well, a long time ago, in '64 already, Hering proposed, that was more or less on heuristics, a color opponency model. And he said we have these small wavelengths, medium wavelengths, and long wavelengths. So that's the scientific name today. We have not red, green, blue, but small, medium, large wavelengths. You take the differences between these two, and if you take all three, you get black and white, and if you take two of them, you get yellow, blue, or red, green. There are animals with more detectors. You know which animal has the most of the different colors? A famous animal that has 4 colors is a mosquito. You know why a mosquito has 4 colors? It also has infrared. So infrared is even longer than the red wavelength. If at night a mosquito lands on my hand, it cannot see anything, but it can see the heat map of my image, of my hand. And there are highways illuminated because that are my blood vessels. And if he is going to land, well, he lands on one of these highways and starts to drill. So he needs to see at night where your blood vessels are. And he can definitely see it. So if you wonder, how can he find me? Snakes do the same. They live at night and they see a warm mouse, clearly illuminated, and the mouse cannot see him, but he can see the snake. Well, the animal with the most color is butterflies. They even have 8 different receptors, so they can go to extremely high derivatives and, let's say, differential structure in color. So if a butterfly lands on a leaf, a petal of a flower, it sees much more than we can see. It can see the age of the nectar. It can see pathways of where the vessels in the petal run and so on. So it's pretty amazing how it can find its way. But he needs that. We don't need that. So that's... Well, the Hering basis turns out to be, if you plot it, it looks like this. And then Koendering said, hey, this is remarkable. That very much looks like, this is the 0-order derivative. It looks like a Gaussian. This thick line looks like a 1st-order derivative, and this dotted line is a 2nd order. So Koendering came with the idea that he said, okay, we can have the same Taylor expansion like in the spatial domain with spatial derivatives. We do the same in the color domain. And we take a derivative in the wavelength. So if you take the 0-order wavelength, this is only luminance. It's centered in the green part. And here you have the 1st-order derivative, and it takes the difference. This is positive, and this is negative. Well, this is bluish, you see, that has the positive part in the bluish area, and the negative part is in the yellow area. So this is a plus blue minus yellow. So this is the blue-yellow differential, and that's why you see it's the 1st order. And the 2nd order is purple-greenness. Well, the negative part is in the middle. That's clearly green. And this has 2 parts, a positive part here and a positive part here. Well, this is a little bit bluish and a little bit reddish, and together that's purple. So that's what we say, it's purple-greenness. Do we have a certain scale? Because these are nanometers. No, it's single scale. So we do not have multi-scale in color. It's 55 nanometer scale that we have differential operators. So let's see what happens if you do really a measurement. Well, of course, we take a measurement with a finite aperture. So we have, again, the whole You remember, finite aperture, it should be a Gaussian, etc. We now measure a certain probe, so we also get color with the spatial scale space. Well, how can we be invariant from all these reflection properties here? That we say, okay, it doesn't matter how we look at the surfaces of the car, it doesn't matter what kind of lamp we have. So we want to be invariant for the physics of how the light emerges from the light reflection to my eye. So we're going to look what happens in these reflections. E is the emittance as a function of lambda. It reflects here, and you have several. This is the normal, and you have here the S and the V factor. This is the incident, and that's the outgoing. And there may be some internal reflections due to the microstructure, and these reflections add up to what kind of color you see. If you have transparency, it goes through it. We don't look at transparency right now. But if you look at the spectrum as a function of lambda, what do we see? Well, first of all, it is dependent on the emission spectrum from the lamp, multiplied by some factor that is the geometry. And it turns out to be 1 minus rho, and rho is a function of the normal and the incident and outgoing directions square. And this is the body reflections measure as a function of wavelength. So that means how much of the wavelength is reflected by, let's say, a red surface. Well, red goes through, but green is, the opposite color is inhibited. So you have the geometry and you have the reflection here. Well, this means that if you have this function that the energy distribution will depend on the position at the imaging plane, so it is also a function of x. So we have x here, and x there, and x there. And now we assume an illumination with a locally constant color. So that means it's kind of a patch, and on that patch we have a locally constant color. What does it mean? That it is separable. So I can say it doesn't matter this E on x, it is just E of lambda times I of x, and then we have the geometry and the reflection. So if I separate it, I get this top formula. How can I make that more or less invariant? Well, the trick is take a derivative. Take the derivative to lambda. So how much is this property dependent if you change a little bit the wavelength? Well, you take the derivative to lambda. You get, because we have a lambda here and a lambda here, we get the chain rule. First, we say we take dE d lambda. That's this one here. And all the other terms are constant, so we keep them in front. Plus, then we keep E lambda, and we take the derivative of the rest, and we get dr omega d lambda. So now we have two equations. We have E, and we have dE d lambda. But as you see, these equations have several terms in common. This whole geometry term is right here, but it's also right here. So if I take the ratio of these two, a lot of this is gone. And that's actually the trick. So the ratio becomes invariant. So if we look at the ratio of E and dE d lambda, so we take dE d lambda divided by E. Now we get this, and you see that all these geometry terms are gone. So we don't have this 1 minus rho, and this was dependent on the angle of incidence, etc. So this means it is independent of the viewpoint, the surface orientation, independent of the illuminance direction, illuminance intensity, and illumination color. That's quite nice. And with this guy, we're going to do some experiments, and we're going to calculate some things. So we can take now derivatives to whatever order, but we take derivatives to space, and we take derivatives to lambda. So this is the spatiochromal invariant. That means it is E hat, that is the ratio, and we take derivatives to lambda and derivatives to m. Of course, we have these Gaussian derivatives, so we convolve with a Gaussian, and the Gaussian is now in the lambda domain. The mean is 550 nanometers, and it has a single sigma 55 nanometers. So it is again a Gaussian convolution, so we can do the whole thing with a kind of a GD-like function, but we do it in the Fourier domain. Later you will see the code, and it's exactly the same. And now we can make, in the same way as we did invariance with our gauge coordinates, we can make the same invariance that we say we combine them with these Laplacian edge detection, curvature detection from all these gauge coordinates. So we can make a whole set of this. Let's give some examples. This is the if you take the illumination color, you see that independent of the type of illumination, you nicely get the edges detected. I go talk a little bit about how this was implemented. I have time, yeah. I initialize my notebook. It's a little bit complicated, but I'll do my best. The first part of this notebook is what I just told in my PowerPoint, so I skip all that. But here I say I have my function E, and here I take the derivative of this function, and I can write it in a more simple. And now you see E of x and lambda is a separable function with this guy of lambda. And now I take here the ratio, d E d lambda, divided by E. So this guy is my invariant. And now I can take all kind of combination with spatial derivatives, and I take it here, the spatial derivative with the derivative to x. So you see, I get some interesting formula. Let's have a look how it looks here in more simple notation. I get here a function, derivative to x and derivative to lambda, derivative to x, and here only derivative to lambda. Here the function itself, square. So now we need to calculate how to find all these kernels, c lambda, cx we know, that's just a spatial derivative. But how can we find this c lambda? This is Koendering's derivative model. He shows that in the... Here we have it. So we have all these three derivatives, 55 nanometer scale. Okay, let's go on faster. Here you see the distribution of colors of an image like this. It has mainly bluish, green and red colors. Okay, but what we now go do is we go to a standard color space. RGB is rather, let's say, arbitrary. It is not perceptually constant. So, as you know, there are quite a few color spaces, and it's interesting to read. Wikipedia has a very nice tutorial on color spaces. Color spaces means, what do you use the colors for? If you use the colors just for visual perception, you need to have a color space that's dedicated to your RGB cones. If you need a color space for, let's say, quantitative measurements, you go more to the XYZ values. And there are matrices that take a triple in color from one space to a triple in color to another space. So that's a 3 by 3 matrix. So if I go from RGB space to XYZ, I go to here. And if you go from XYZ space to our E space, you get this. And this is actually the matrix we put on all our incoming images to be in this E space. It was proposed by Jan-Mark Geuzenbroek some years ago, and it is still very much used. If you look at the columns of these receptive of this matrix, you see actually that we already begin to recognize the three derivatives. This is the zero order, that's just a Gaussian. This goes up, 0 goes down. This goes up, goes down, goes up. So we see the 0 first and second order derivative already coming up here. So this is the receptive field. And now we implement the whole thing. Let's take a few minutes on how that is done. I import an image, and this image clearly has color edges. It has intensity edges and it has color edges. This, for example, is a color edge from green to green, and this is a color edge from green to red. So if I make a green-red detector, it will see nothing here, but a lot here. If I look at intensity, I can find this one. So this is an intensity change, and this is a color change. Let's have a look at the data. The data is 228 by 179, and it has a triple. It's a color image. Now I define my color receptive fields. That's a triple of these three columns. And now we map this color RF, this matrix, on every pixel by mapping the dot product. So we do the dot product with this matrix on every pixel. So every pixel is now moved into our new space. This means we do that at the second level, not on the rows, but we do it on what's inside the rows. These are the single pixels. So we call this now the observed image because it has been taken by this receptive field. If you look at these images, how they look like, we can calculate them. And here you see the original image. This is the image seen by the zero-order derivative, the first-order derivative, and the second-order derivative. And you see already some interesting things that it is quite different. Here you see a lot of sharp contrast between the blue and the green. Here you see a good contrast between the blue and the yellow. So let's take our ratio, the d lambda E divided by E, and we call that big epsilon. And if we now take the derivative of this big epsilon, we get this complicated term. Let's define some short notation term and then take the derivative, in this case to y. And you see we get all these mixed derivatives, first to y, then to lambda, and you can take all the different combinations. Here you have, for example, the derivative to x squared plus the derivative to y squared. That's the gradient magnitude. Well, it turns out a quite special one. We need that a lot. So that detects intensity edges in the spatial chromatic domain. So we get this formula. We can also take the intensity edge with the derivative to lambda. Anyway, we make a lot of these. Oh my goodness, it's the 5th of December. I'll stop in 5 minutes and then you can get some paper notes downstairs. If we look at this derivative, you see it is derivative to x and y and lambda. First time to x, 0 to y, 2 times to lambda. How it is implemented in Mathematica with the function derivative. How many times to e, to x, y, and lambda. Well, now we get a very... if I have this invariance, that was my derivative, and n, just an example, it's called the total edge strength. So n is it is the gradient in the x direction, and it is the gradient in the x lambda direction. Quite a complicated thing. I call that called n. You see, it's quite a big formula, so we're going to not do this by hand, but we let Mathematica do the implementations by substitutions, which this replace. So we clear the whole thing, and then we say we take this n with all the derivatives inside, and we replace all these derivatives by these derivatives of my receptive field. And here are all these derivatives of my receptive field. But finally, I need to make an implementation that I say, okay, I have all my derivatives here. These are the derivatives to color, taken from my columns from the matrix that I just showed you. But we also have these spatial derivatives. So in this case, derivative to x. So we need to make the spatial derivatives to x and y, do another one, and we replace them by our standard GD, as we have always seen. So we replace this now. And now we get a combination that we have the color receptive fields and the spatial receptive fields in one thing. And this can be calculated. So if I now calculate this on my image, you see that I very nice get not intensity edges, but I get color edges here. So you see there's hardly anything visible here. And you can now calculate all of these very nice combinations of spatial derivatives and spectral derivatives. And I programmed the whole thing before you, so everything is in a nice notebook, and you can just see that there's a lot of code, but all these things are being implemented. You can actually use them. Let's use them. This is a yellow-blue detector. It's called G. So I take the derivative of the yellow-blue detector from this image. And what we see is quite remarkable. You see that I do not get intensity edges. So this black and white, it's a very strong edge. It's completely invisible here. So I really do not look like that. I do not look at intensity edges, but I only look at color edges. And of course, here the yellow-blue I get very strikingly. So now we have a new means of looking at structure in images, not just look at the pixels and intensities, not even look at color intensities, but look at specific wavelength differences. And that's what your eye does too. So it's a new way of thinking. We don't look at RGB and these intensities and so on, but we really look at spectral differences. So that's where we take yellow, blue, and red, green derivatives. Anyway, there are lots of more examples here. You see there is only a color edge, and there is not an intensity edge. And now you see we can get this. It's perfect time for me to stop here. In the PowerPoint are still a couple of examples that we show. People have used this a lot for, of course, the staining analysis from all these blood cells. Of course, we do this now with deep learning, but this course is what does the deep learning actually do? So we can run it and it works. And we saw in the first lecture by Mitko Vetko that it is really efficient. But if you really want to look under the hood what's happening, we see that we have now added a new differential structure. So we not only look at edges, corners, derivatives, and the whole thing, we look at spectral derivatives. So now you can do different types of staining and all these spectral. So now you want to find only these specific color differences. Here you find them. And underwater, if you see how a color analysis by a deep learning network, what types of filter it takes, we saw that from the Grzewski. It takes exactly these color derivatives filters. So they are in there. And now you understand what they do. They also have an invariant structure. You can build invariants from them that are independent from illumination changes, from spectral influences. So it's quite powerful. Okay, we saw this before, and people have done this now on many more images. Suppose you take 3 measurements from MRI, T1 weighted, T2 weighted, and proton density weighted, from the same anatomical object. This is a transversal slice of a brain. You can use this T1, T2, and proton density as RGB, and then run all these color invariants. And then you nicely see that this is a super way to find, for example, the edges between the white and the gray matter, because you look at specific contracts. So we don't look at intensities, but we use now the full 3 modality information. And this is also one of the things I want you to have a look at. Okay, so color space is compatible with the classical luminance space. So we have derivatives, we have Gaussian. It's not multi-scale, it is 1 scale. This model, because we look at the ratio between the derivative of a property and the property itself, we kick out a lot of geometrical properties. So we are invariant for the illumination. And we can build differential operators, and they emerge in the first convolutional neural networks layers as well as in cortical V1. So thank you very much. Let's have a small break, run to the paper note, to the coffee, and I'll see you back in 15 minutes.